today's lesson by going over this problem from your opener. So the directions in the opener asked you to write a brief story that could potentially describe this graph. Well, my story that I chose to use to describe the graph is some girl named Amy is riding her bicycle. So if you'll notice, the graph is labeled, the x-axis is time and the y-axis is distance. So this is what we call a distance time graph. So there's a few things that I want to look at regarding this graph. So first, I want to ask you, if Amy's riding her bicycle, is she going at constant speed throughout her entire journey? Well, if we look at the graph, we see that there's actually three distinct portions of the graph, and they each have a different slope. Whenever you look at a distance time graph, a change in slope relates to a change in speed. So the first little section of our graph is from time 0 to 15. The second portion of our graph is from time 15 to 30. And the last portion of our graph is from time 30 to 60. We can also see that during each of those portions of time, Amy traveled a particular amount of distance. So if I want to see what her distance is at 5 minutes, we need to go to time 5 and go up to the graph and see that she traveled a total of 2 miles during those 5 minutes. If I want to see what Amy's distance was at 20 minutes, I go to 20 on the x-axis, follow that all the way up until I hit the graph. We notice that that lands on 6. So here Amy traveled 6 miles. And if I want to see what Amy's distance was at 60 minutes, I'm going to go to 60 minutes on the x-axis, go all the way up until I hit the graph, and we see that that is 8 miles. So there's something that I want to look at regarding each portion of this graph. Let's go back to slopes for a minute. If I ask you to write an equation for the different parts of her trip, we're going to need the slope, right? So looking at this first portion, this blue portion right here, in order to find the slope, we're going to look at the rise over the run. So if I start here, I can go up 1, 2, over 1. So my rise over run in this case is 2. Let's see if it follows that pattern. Up 1, 2, over 1, up 1, 2, over 1. So for this whole portion right here, Amy is going at a speed of 2 miles per minute. Okay, if we look at this next portion, my red section of the graph, I don't go up or down any. All I do is move horizontally. So if you'll remember, if I have just a horizontal line, that's what we call a slope of 0. So it looks like Amy was sitting still on this portion of her journey. So the first portion, she was pedaling really, really fast. She was going 2 miles per minute. And then the next portion, she decided to take maybe a water break and she was sitting still. The last section, the green section, it looks like Amy slowed down a little bit compared to the very first section. So if we'll go up 1 over 1, 2, 3, up 1 over 1, 2, 3, I see that Amy is going 1/3 of a mile per minute. So these are the three different speeds, and we can use those slopes to write equations for the different parts of her trip. However, would it be possible to write some equation for this graph that's just one single function? We broke it up into 3 separate functions, but can I write it as one? And that's what we're going to be looking at today. So today's lesson is all about what we call piecewise functions. Piecewise functions are just pieces of different functions that are all on one graph. So think about some of the functions that we know. We know quadratic functions. So let's say I graph a quadratic. We know linear functions. So let's say that I have some linear function. And we've also talked about absolute value functions. So let's say that I have some absolute value function here. But piecewise functions are kind of piecing together the functions that we know. So kind of think of, we have our functions, but we're going to erase portions of them and join them with different functions. So let's say that I want to stop this graph here and pick back up with my linear graph here, and let's say, but I want it to stop here and then pick up with my absolute value graph there. So we see that we have particular places where the graph is going to be defined. So just think of a piecewise function as pieces of different functions all thrown together. All right, so let's say, for example, that I have a function that is defined using these following criteria right here. So when x is between -3 and 2, f of x is going to be x squared. We know that x squared is a quadratic function, meaning it's going to be shaped like a u. However, it's only between the points -3 and 2. So I know that -3, I'm going to start my graph, and at 2, I'm going to stop my graph. Let me fix something real quick, and y'all see why in just a second. So it's still going to follow the general shape of the graph, but it's going to be restricted by these points. So can I write the domain of just this section right here? If you remember, the domain is all of your x values. So I know that I have from -3 to +2 is where my function is. So we can say from -3 to +2. Now, why did I use less than instead of less than or equal to? Well, that's because I have open circles here, so it's not defined at that particular point. It's less than 3, but it's not, or less than -3, but it's not equal to -3. Now, the second part of my graph says when x is greater than or equal to 2, so I'm going to start at 2, but it's less than 6, I'm going to have the line x plus 2. So I know that this is a linear function, so it's going to be a straight line, and I'm going to start here, and we're going to end at 6. So it's going to look something like that. However, this says x is greater than or equal to 2, so I need a closed dot at 2 because it's defined there. So if I were to write the domain of just this function, my x values go from 2 to 6. So I start at 2, and remember that is defined there because it says or equal to, but less than 6. Not defined there, so it's just a less than symbol and an open circle. So if I wanted to write an equation for this as one function, we can combine these rules. So this is going to look a little weird, just bear with me for a second. So I can say that f of x is equal to, I'm combining two functions, so I want to use a little curly bracket here. My first function was x squared, and my second function was x plus 2. But we had certain criteria. It wasn't the whole x squared graph, because that would have gone forever in both directions, and it wasn't the whole x plus 2 graph, because that would have been a straight line forever and ever in both directions as well. So we need to include our domains. So next to the x squared, I'm going to say -3 is less than x is less than 2. And here I'm going to say 2 is less than or equal to x is less than 6. So this is how you would write it, and it looks kind of weird, but all this is saying is that I'm combining the function x squared and the function x plus 2 given these restrictions. So another thing that we can do with these graphs is we can evaluate them to fill in a table. So here I have my function just like we defined last time. Okay, so if I want to fill in the pieces of this graph, or this table, okay, I need to look at, just like when we were looking at Amy's bicycle journey, if I wanted to know what her distance was after 5 minutes, I would go to the 5 on the x-axis and go up until I reached the graph. Same thing here. If I want to define f of -3, I'm going to go to my graph at -3 and then go all the way up until I reach the y value, but notice that this is an open circle. Does that mean that -3 is included on my graph if it's an open circle? No. So this is actually what we call undefined. So I'm just going to write the abbreviated undefined. Okay, what about -2? If I go to -2 and go up, I reach this point right here, which is 4. So my graph is defined here. Okay, and I'm still in this x squared portion, if you'll notice, because I'm still getting my answers from the orange graph. -1 is at 1. 0 is at 0. 1 is at 1. But notice what happens when I get to 2. If I go to 2, remember that's no longer defined by my orange graph, my x squared, because that was an open circle, but it is filled in by that purple graph, which was x plus 2. So I do have an answer to this. It's going to be 4. If I go to 3 and go up, that's going to be at 5. If I go to 4 and go up, that's going to be at 6. If I go to 5 and go up, that's at 7. But notice what happens when I go to 6. I hit an open circle. So remember we said that x is less than 6. It doesn't include 6. So again, this is going to be undefined.